All right. We'll go ahead and get started today. So, right, last time we left off our discussion, thermodynamics, talking about enthalpy, talking about standard enthalpy changes at certain temperatures and such. And we'll start off today with just kind of talking briefly about how enthalpy can vary with changes in temperature. Okay, so depending on kind of the temperature. All right. Apparently my audio is muted. I don't know for how long, but hopefully not too long. All right. But yeah, so again, right, that change in enthalpy is related with the heat capacity times some change in temperature. Okay. And so if we consider some change in enthalpy related to some change in temperature, right? So enthalpy at one temperature minus enthalpy of another temperature, right? It's just related within the integral, right, of that heat capacity over that temperature range. Okay, so I'd integrate that from T1 to T2. Now, using that idea, right? Again, that some change in enthalpy is just related with the change in temperature and heat capacity. Okay. If I consider now, instead of like enthalpy at temperature 2 and enthalpy at temperature 1, instead if I consider, say, the enthalpy change of my reaction at temperature 1 and enthalpy change of my reaction at temperature 2, which is related with enthalpy of the products at temperature 1 minus the enthalpy of the reactants at temperature 1 and temperature 2, right? Right? So if I consider that, and then the fact that what we're interested in answering, right, is how does the enthalpy change of my reaction change with temperature, right? So that's why I have this like delta H, right? This change and a change in enthalpy, right? A change in the change in enthalpy of your reaction, right? Which again is just the difference in the change in enthalpy of your reaction at T2 and at T1. Okay. Questions about this so far? Yeah. Right. And so using that, I can kind of expand out what delta HT2 is and delta HT1 is, again, from this previous slide here. Okay. And then just rearranging things, putting the products together, the reactants together. Okay. And then using that kind of definition we talked about at the very beginning, right? That the enthalpy change, the enthalpy at T2 minus the enthalpy at T1, just related to the integral of that heat capacity times dt. Okay. The heat capacity here, that subscript P, is just meaning under constant pressure conditions, which again, reactions are typically under constant pressure conditions, so that's why we use the heat capacity under constant pressure. Okay. And so that change in the enthalpy change of our reaction, right? That's what that delta H is standing for, is the change in the enthalpy change of our reaction based off the change in temperature, is then just related with the integral of the heat capacity of the products minus that of the reactants. Okay. So this is often written as kind of this, okay? This integral of this change in heat capacity between products and reactants. Now, assuming that change in heat capacity is constant, okay? Okay. Assuming that change in heat capacity is constant, it's temperature independent, then doing this integral of delta Cp dt, where delta Cp is a constant, just simplifies down to delta Cp delta T. Okay. So this is the final kind of equation that's typically used for Kirchhoff's law here, where again the change in enthalpy for a reaction with respect to a change in temperature is by the change in temperature times the change in heat capacity of that reaction, which is, again, the heat capacity of the products minus that of the reactants multiplied by their stoichiometric coefficients. Okay. So again, essentially what this is saying, right, is if I have some chemical reaction and I increase the temperature of that chemical reaction and the heat capacity of the products is greater than that of the reactants, then the enthalpy change for the reaction should increase, right? Okay. Right, essentially, totally kind of what this is getting at here. All right, if I imagine plotting, there it is. All right, if I imagine plotting, okay, say I have the enthalpy of my products, say I have the enthalpy of my reactants, right? At some T1, okay? Now, if Cp products is greater than Cp reactants, okay, right? Cp product being greater than Cp reactants, what that means is that at some higher temperature T2, right, there will be a greater change in enthalpy for the products than there will be for the reactants, right? Because if I want to get my products from temperature 1 to temperature 2, I got to add some amount of heat to get there, right? Well, Cp of the products being greater than Cp of the reactants is telling me it takes more heat to increase in order to increase the temperature of those products than it does for the reactants. So basically, this increases by some amount, and then this guy increases by less, right? And so again, what we're interested in is the difference in enthalpy of the products minus the reactants. That's the delta H of the reaction, okay? Right? And in this case, the delta H of that reaction, right, at T2 happens to be smaller than that of T1 for this specific example I gave, right? And it's not always the case that delta H at a higher temperature for a reaction is smaller than that at a lower temperature, but in this example, it is, right? Right. So I'm just kind of trying to re-represent this idea of what the heck is delta H looking at, right? And delta H is trying to look at what is the change. I'll put the little R here, right? What is that change in the enthalpy of my reaction between temperature 1 here and temperature 2? Okay. Questions? Yep. Mm-hmm. This? Oh, this VI here? Yeah. Oh, yeah, sorry. That is the stoichiometric coefficients in your balanced chemical reaction. Oh, right. Sorry, that was, I was thinking, so the M there is standing for molar heat capacity, right? So for heat capacities, the heat capacity itself is, so for example, Cp is the constant pressure heat capacity, right? Which again is under constant pressure conditions, how much temperature does it change to raise, or how much energy does it change to raise the temperature of your substance by 1 degree Kelvin? What that's getting at. This is an extensive quantity, right? It depends on the total amount of stuff you have. CPM is the constant pressure molar, I guess you'd pronounce it molar constant pressure heat capacity, but the molar heat capacity, all that is, and this is an intensive quantity, basically CPM equals Cp divided by N, okay, or N is your number of moles, right, of your substance. And so CPMI or whatever, right, this guy here is saying the constant pressure heat capacity, the molar constant pressure heat capacity for compound I, reactant I, right? And then V sub I is the stoichiometric coefficient of, say, reactant or product I. Okay. The reason why I wrote it using this is often in tables you're given molar heat capacities, right? Because you don't know how much total stuff you have, right? If you're making a table, you want to use intensive quantities and not extensive quantities. So often in tables when you're looking up heat capacities, you're looking up molar heat capacities, which are the heat capacities divided by the number of moles, right? Or the heat capacity per mole, right? So the molar constant pressure heat capacity is how much energy is required to raise the temperature of 1 mole of your compound by 1 degree Kelvin, right? And then again, the V sub I here is like a stoichiometric coefficient. So if your reaction, right, was 3H2 plus N2 going to 2NH3, right? The stoichiometric coefficient for H2 would be 3, N2 would be 1, and NH3 would be 2, right? That ammonia formation reaction, right? So, yeah, so the V sub I would just be the stoichiometric coefficients for your products and your reactants. Other questions about this formula? So again, often, right, unless your reaction enthalpy is very small to begin with, or the temperature change you're interested in is very large, this change in the reaction enthalpy is typically not too significant. That often you're not going to worry about this if you're going from 298 Kelvin to 315 Kelvin or something like that, right? Like small temperature ranges aren't going to be that relevant for this. Again, unless the enthalpy change for your reaction happens to be like 0.1 kcals per mole or something like that, right? And maybe at one temperature it's endothermic and another temperature it's exothermic, right? Depending on how big that is. But so often one doesn't necessarily concern themselves with this, but it can be relevant. And this is more relevant, obviously, in a lot more, say, chemical engineering applications. If you're trying to understand, how to optimize some chemical reaction under potentially high temperature conditions or things like that, right? And you're looking up enthalpies, informations from low temperature, right? If you're running some reaction at 3000 Kelvin, but you only have 298 Kelvin enthalpies of reactions and things like that, you'd use this formula to get what the actual enthalpy changes for that reaction at 3000 Kelvin. All right. Any other questions about this? Some example of this, right? So here, just kind of a simple example. Consider the standard formation reaction, right, for gaseous water. So forming H2O gas from H2O2 gas. Okay. So for that reaction, the standard entropy of formation happens to be 241.82 kilojoules, right? At 298 Kelvin, what is the entropy of formation at 392 Kelvin, given the following molar heat capacity values? All right, so if we're trying to solve this, right, trying to get that change in entropy respect to change in temperature, okay? So we're going to use, again, this formula here, delta H is equal to delta Cp times delta T, right? So we got to write out that formation reaction, which is H2 gas plus 1/2 O2 gas going to 1 H2O gas. Now, I didn't write this as 2 H2 gas plus O2 gas going to 2 H2O, because in the problem you're given the enthalpy of formation, which again is related to this formation reaction, which always has the stoichiometric coefficient of the product equal to 1. And so if you used this reaction and multiplied everything by 2, you need to multiply the enthalpy given in the problem by 2 as well. Okay. For example, right, the enthalpy at 298 Kelvin given was minus 241.82 kilojoules. You'd have to multiply that by 2 if you multiplied this entire chemical reaction by 2. And then otherwise, things would work out just fine. For the most part, you just have to divide your final answer by 2 as well. So it's, yeah. As long as you keep track of your factors of 2, you could have worked out the problem given different stoichiometric coefficients in the chemical reaction above. Okay. But yeah. Assuming this is the reaction you wrote out, right? Again, that change in enthalpy with respect to change in temperature, looking at the enthalpy at 392 Kelvin minus the enthalpy of 298 Kelvin, which is equal to delta Cp delta T. Well, we just add that enthalpy at 298 Kelvin onto the other side. Okay. That change in temperature is just 392 minus 298, which happens to give you 94 Kelvin. Okay. And then I just got to plug in for the Cp of my product, H2O, minus the Cp of my reactant H2, minus the Cp of my reactant O2, multiplied by its stoichiometric coefficient of 1/2. Okay. So that's where that 1/2 comes from. So you're just plugging in those numbers that are given, right? Simplifying the problem a little bit. Okay. Now note that these enthalpy, these heat capacities, right? Come back to the original question, right? The heat capacities are given in terms of joules per Kelvin mole, while the enthalpy changes in terms of kilojoules per Kelvin mole. Okay. So we need to change this 934.83 joules to kilojoules by, say, dividing it by 1,000. And then when you do that, you get this final answer, minus 242.76 kilojoules, right? So as you see, right, basically there's about 1 kilojoule change in the enthalpy of this reaction for almost 100 degrees Celsius change, right? So depending on what you're doing, that 1 kilojoule change in the enthalpy of the reaction might not be that relevant or important to you, right? Okay. But yeah, so again, it very much depends on the temperature range that you're interested in, what the enthalpy that you're interested in is initially. Okay. Because again, if somehow the reaction enthalpy for this reaction was around 1 kilojoule to start off with, then a 1 kilojoule change would be 100% change in the reaction enthalpy, right? But in this case, right, going from 241 to 242, right, it is a 0.5% change. Okay, so not a very large change, right, in the total enthalpy of the reaction. Yep.
Why is the delta H at 298 negative? Can you move it over to the right side?
Oh, because the negative sign got left up here. My gosh, I did not notice that right in the problem. Yeah, this is negative 241.82. That minus sign is, yeah, I do, yeah. Yeah, so, yeah, that was, really should have been down below. So it was negative 241 kilojoules. And then this also, I don't know why I started writing 373. Nope. Numlock is off. These should be 92 as well. So yeah, so that negative sign was, yeah, it was supposed to be there and obvious, but I mean, it was there, it just wasn't very obvious with how it was written because of where PowerPoint broke the line. So I apologize for that. Other questions? All right, so that does it for enthalpy. And so now let's start talking about entropy. And we're going to talk about Gibbs free energy. And then we'll finish up with talking about kind of equilibria and things of that nature, both phase and chemical and electrochemistry. So As just a reminder, again, we're going to kind of go through some of these things, especially some things that hopefully have been introduced to you before, right? Concept of entropy is hopefully not new, right? Again, the idea of entropy is related with spontaneity, okay? Right, spontaneity, right, is just if a process is spontaneous, it occurs without any outside intervention, okay? And any process that is spontaneous in one direction will be non-spontaneous in the reverse direction, right? Again, just imagine a ball rolling down a hill. Ball rolling down the hill, spontaneous. Up the hill, not spontaneous, right? Nothing is spontaneous in both directions, right? Okay. Right. So yeah, right, and again, in this example, right, you can imagine a gas expanding into a vacuum. That will happen spontaneously, but the gas will not go back all to one side spontaneously, right? You're never going to have all the gas molecules in this room congregate to one side of the room, right, such that the other side of the room has a vacuum, right? That would not be good for our health if that occurred, okay? Right, so again, spontaneous in one way only, okay? Right, so entropy itself is related to spontaneity, and entropy is the measure of kind of the dispersion, the disorder of matter and energy. Okay? So the more energy is dispersed in your system, right, across all molecules, the more random and chaotic the motions and locations of your molecules are, the greater the entropy is for that system. Okay? So again, I have an example of, roughly a perfect crystal versus some crystal with kind of disorder and things kind of rotated around a little bit, right? Okay. In which case the left side has lower entropy than the right, okay? And then here, right, if you have some high temperature, low temperature object, right, in this situation, right, you have an overall lower entropy system compared to if this thing equilibrated and some of the energy was transferred from the high temperature to low temperature, and this would be at equal temperatures between the two, right? And that will have a greater entropy than the system up above because the energy is dispersed over more molecules, more things. Okay? The more you disperse your energy over more things, the greater the entropy, okay? Which again is part of the driving force for the idea of thermal equilibrium, right? If things reaching the same temperature, okay, that's a spontaneous process, and a lot of the reason why that spontaneously occurs is due to entropy. Okay? The fact that you increase the entropy when you transfer that energy equally across all things. Oh yeah. So well, the wall here is called diathermic, just because it allows the flow of energy between two sides. Okay. So an adiabatic container, right, does not allow energy to flow between them, right? Doesn't allow heat to transfer, right? A diathermic wall, which is just anything that's not adiabatic, allows heat to transfer through, right? Right. So like a plastic coffee mug versus styrofoam or something like that, or paper cup, I guess, right? Putting coffee in a paper cup, potentially going to burn your hands because the container of that paper cup would be very diathermic, right? A lot of energy easily flow through it, versus a styrofoam cup does allow energy to flow through it. So yeah. Right, and different ways that energy can be stored in your system is through vibrational motion and rotational motion, right? And so the larger your molecule is, the more different types of vibrational motion you have, right? So the more potential entropy that molecule has compared to some smaller molecule, because there's more different ways to disperse its energy versus, say, in water, the example of water here, It's only got 3 vibrational modes in which it can put its energy in. Okay, but if you have a much larger molecule, you have many more vibrational modes you can spread the energy out into. So again, the more molecules, the more ways you can spread your energy out, the more entropy you're going to have. Okay, right? It's why things like dissolving things in solution, even if it's endothermic, can be a spontaneous process, because this idea of entropy, right, and the fact that if I had these perfectly separated layers, right, there's a lot less disorder than that than if I mix these 2 layers together, right, and disperse a bunch of the solid within the water, right? And that dispersion of the solid into the water creates much greater entropy in your system, and that can drive this thing to happen spontaneously, even if it happens to be endothermic. All right, so there's some quick little practices, right, for entropy, okay? All right, so if I had, say, 1 mole of oxygen gas or 2 moles of oxygen gas, which is going to have greater entropy? Two moles. Or 2 moles, right? So it's going to be 2 moles of O2 gas will have greater entropy than 1 mole. And that's because you just got more stuff to move around to get into, you know, more variety of locations and variety of distributions of your molecules, okay? And in general, right, entropy is an extensive quantity, just like enthalpy, just like internal energy. These are extensive quantities. The more stuff you have, the more entropy, enthalpy, internal energy, Gibbs free energy that you have, right? All of these things are extensive, so they will be larger values the more stuff you end up having.
Entropy does not depend on the volume, like where the gas is confined or something?
The entropy of the gas depends on the volume it's contained in. Yes, it can. Yeah, but it's dependent on volume versus total amount. It is not like equal, right? If these 2 gases were in the same volume, it would. I think you'd have to have the 2 moles in a much smaller volume, maybe. But then you have such high pressure, if it different temperature. Yeah, I mean, you need the temperatures to be the same. Trying to think how this would work with volume change. Those 2 moles, change the pressure.
Gas is always in like closed container.
Yeah.
So it should be like, when I was seeing this question, I was thinking like, what was the volume? If the volume is same, then the first one is have more entropy than the second one. If it's open, then you can say that other one is more.
Yeah, right. If it's open, right, the second one takes up more volume, so it has more entropy, right? Yeah, again, entropy is if I had a constant temperature system, change the volume, the gas, occupy that, decrease that. Yeah, I'll have to think about that, right? Because I can use a calculator. I'm just not sure if I would need to know what is the molar entropy of just O2 gas, like what is the natural entropy. So entropy, this is right. Entropy is an extensive quantity, and where's the not second law? Third law of thermodynamics. Right, the entropy, things have absolute entropies. Okay, so the third law of thermodynamics states that a perfect crystal at 0 Kelvin has 0 entropy. Okay, so at absolute 0, a perfect crystal of a pure element or compound has an entropy of 0. Okay, which means that the entropy that there's a defined minimum value, just like 0 Kelvin is like defined minimum value for temperature, right? And so every molecule has some sort of absolute entropy, right? And so kind of what you were getting at here, right? If they're in the same volume, right? This has twice the sort of absolute entropy. 2 moles of O2 has twice the absolute entropy of 1 mole of O2, right? But for say an ideal gas, if we treated these as an ideal gas, right? A decrease in volume causes a decrease in the entropy, right? And so the main thing is I would need to kind of know what is the initial molar entropy of 1 mole of O2, and then figure out, okay, I have twice the molar entropy for the guy on the right than I do on the left, okay? But then the question is, right, how much is the entropy decreased because I've now, let's say, compacted my 2 moles of O2 into the same volume as 1 mole. And so, yeah, I guess I thought that in too much detail. In my head, I was thinking open container, but I didn't write it down. But you're right. If these are in the same volume, there's a chance that, say, 1 mole O2 could have a greater entropy than 2 moles of O2. I don't know exactly what those numbers would have to kind of be and come out to be for that to happen, but it is potentially possible. All right, for the next example, just O2 gas versus O2 liquid, however much quantity you want to think of. Yeah, the gas, right? Gas, you have things much more spread out, moving around, a lot more chaotic, right, than the liquid, obviously. All right, and then sodium chloride solid versus sodium chloride dissolved in solution. All right, this second one, right, dissolved in solution. All right. 1 mole O2 gas versus 1 mole O3 gas. Yeah, O3, you have more, yeah, you have more degrees of freedom, more ways that this molecule can orient itself, more vibrational states that energy can be thrown into, right? And then similarly, CH4 versus C2H6, right, would be, yeah, C2H6 as well, right? That I have a larger molecule, right? Again, if anything, you could just think of the idea that, again, entropy is extensive, so the more stuff I have, right, the larger the molecule is, the more entropy that you have per molecule, right? And so C2H6 and O3 both have greater entropy than, say, O2 and CH4. We won't really get to calculating entropy and things like that so much in this class. It's just a path I don't want to go down. But I'll just mention that the definition of entropy is that some small change in entropy is related with some reversible heat transfer divided by temperature. Okay, right? A reversible change in state is a change in state where everything is at equilibrium at all times. Okay. We might talk about reversibility. We probably will when we talk about equilibrium and stuff a little bit later. So I'll just, again, mention, right, that a reversible process, everything is always in equilibrium as you're changing stuff. Okay, right. So if you have to be mechanical equilibrium, right? Same pressure everywhere. Okay, thermal equilibrium potentially, same temperature, right? And stuff like that, right? Chemical equilibrium, same chemical potential everywhere, right? Right. That's the definition of something in equilibrium, and a reversible change is when you maintain equilibrium while you do your changes in state. Okay. If you do something reversibly, that's going to give you the maximum amount of work potentially out of a process and such. Okay. But again, a lot of that stuff we won't focus too much on in this class, but just want to mention it. Okay. And then again, as we've been talking about, right, entropy itself is an extensive function. And like enthalpy, like internal energy, like Gibbs free energy, is a state function, right? So it just cares about what are the initial and final states, and not how did I do that change to get to those states. Okay. Yep.
Yeah. I just want to clear my mind. I'm a little confused why sometimes it's like ds and sometimes it's like delta s.
Yeah. So ds is just referring to some like infinitesimal change in entropy. So right, typically how I would get the delta S is, right, if I were to And since this is not really a math class, I myself just flip between them often. But ds, right, saying dq divided by t, right? This is some small infinitesimal change in entropy, okay? How I'd get the delta S form is I'd integrate, right, ds, and integrate dq over t, okay? And then this would give me some delta S equals integral dq reversible over t, I guess, right? And I know the integral of ds is going to give me delta S because S is a state function, right? So it doesn't matter what path I'm taking when I'm integrating this out. I know that the change only depends on what is the initial and final state, right? Where delta S, right, is S final minus S initial, right? And so, yeah, that's how I get, say, the delta S version of things from like that ds, yeah. Other questions? All right. And so the second law of thermodynamics is related with entropy, and it's just saying for an isolated system, an increase in the entropy in your system corresponds to a spontaneous change, okay? And for something that's not isolated, a spontaneous change corresponds to an increase in the change in entropy of the universe, okay? Right, again, an isolated system is when you have no energy and no matter exchange between your system and the surrounding. So in that case, right, the surrounding entropy change is just zero, right? Because again, whatever's going on in your system is not affecting the surroundings. So its change in entropy, its change in state is nothing, right? And so then the entropy change in the universe and the entropy change in the system are the same for an isolated system, okay? But in general, if your system is not isolated, then it's that the entropy change in the universe being greater than zero gives us a spontaneous process. Okay? Right. Again, I'm just reminding again what our definition is of entropy. Again, to solve this, you would need to find a reversible path that connects your initial and final states. But we're not going to go through and do all kind of that stuff and whatnot in this class. So I'll just kind of mention it as a refresher, but we don't need to really worry about that. Mainly we're focusing on what is entropy, what things have greater or less entropy, what are our laws of thermodynamics. Okay. I guess I'll mention, right, that delta S is a state function, okay, but the change in entropy of the system and the surroundings are not always equal, okay? They're only equal and opposite when you're dealing with a reversible process. When things are maintaining equilibrium everywhere, then the entropy change in the system and the surroundings are equal, okay? And that means the entropy change in the universe is equal to zero, okay? We'll see kind of this pop up again when we talk about Gibbs free energies. We'll talk about that third law of thermodynamics. Right. Okay. So, all right. So again, the third law of thermodynamics again is just stating that, what is the zero value of entropy? Okay, which means everything has some absolute entropy that we could experimentally determine or calculate. Okay, and so if I want to get the entropy change for a chemical reaction, often I use this formula here. Okay. Change it so it's all on one line real quick. Let me see the cursor. Right, there you go. Right, so right, so to get the entropy change for a reaction, often you use standard entropies, okay? The SI sub naught are these standard entropies for some compound or some element, okay? of species I, right? The V sub i's are, again, our stoichiometric coefficients in your chemical reaction. So again, this has the same kind of structure as the enthalpy change for a reaction, okay, that we talked about last week. Okay, that the enthalpy change for a reaction was the enthalpy of the products minus that of the reactants multiplied by their stoichiometric coefficients. Here, right, the entropy change for a reaction is the standard entropy of the products minus that, sorry, of the reactants multiplied by their stoichiometric coefficients. And again, because of the third law of thermodynamics, right, these entropies are not entropy of formations. They don't correspond to some formation reaction. They're absolute entropies, okay? Right, it's the total entropy that that molecule has at that temperature, okay? In whatever phase it's in. Which means, again, that things like O2 has an actual absolute entropy and not an entropy of formation of 0, for example. So questions kind of about entropy, okay?
So we have that the work is done by the system or the surrounding, or when the reaction is endothermic, the sign will be negative, and when endothermic, the sign will be positive. How about the entropy?
Yeah, so what are the two terms? It's exogeric. Crap, I'm trying to remember that there's like a terms like endothermic and exothermic for entropy. It's exothermic and
So what is the entropy?
crap. I can't remember. But anyways, but I mean, yeah, you can have a positive delta S, negative delta S, right? Positive delta S means an increase in entropy in your system. Okay, positive change in entropy, right? And then negative delta S of the reaction is right, a lowering entropy in the system, right, which is not ideal, right? So for chemical reactions, right, we want an exothermic reaction is more ideal, right? You want to lower the energy of your system, right? For entropy, right, you want to increase entropy, right? Because again, an increase in entropy for the universe, right, corresponds to a spontaneous process, right? So things spontaneously want to get to higher and higher entropies. Okay, and so that's true for your system, right? Your system does want to get to higher and higher entropies, right, while also getting to lower and lower energies, right? And so we'll talk about Gibbs free energy, right, which is kind of combining those two things to allow us to overall predict spontaneity, right? Does that sort of answer your question?
Yeah.
I'm not sure. Okay. Right. And so yeah, so I want to talk about Gibbs free energy here, right? Okay. So, right, we in the second law of thermodynamics, right, it talks about how the entropy change in the universe is greater than 0 for a spontaneous process, which is related to the entropy change in the system, the surroundings. Okay, but we don't really want to measure the entropy change in the surroundings. We'd like to be able to focus on what is the entropy change in the universe, right? And that's where Gibbs free energy comes from, right? So if I consider some sort of constant temperature, constant pressure system, like most chemical reactions are, right? Most chemical reactions are done under constant pressure, constant temperature conditions, right? Okay, then I can go through, and I'm gonna kind of cut to the end here, but basically what I can do is relate the entropy change of the universe, okay, to two things in the system, the entropy in the system and the enthalpy of the system, okay? And I get that enthalpy of the system because at constant temperature pressure conditions, the enthalpy change in the system is related with the heat transferred in the system and the surroundings, okay? Don't worry too much about kind of this derivation, things like that, just kind of there to show you why we define the Gibbs free energy the way we do, okay? But basically, so for a spontaneous reaction, right, that has some change in entropy, the universe greater than or equal to 0, under constant temperature pressure conditions, that entropy change in the universe is also related to some entropy change in the system minus the enthalpy change in the system divided by temperature. Multiply both sides by temperature and by -1 gives me this relationship here, okay, that for a spontaneous process, dH minus TdS is less than 0. So what I'm going to do is I'm going to define Gibbs free energy as just H minus Ts. Okay. And so under constant temperature conditions, dG, this change in Gibbs free energy related to change in enthalpy minus temperature times the change in entropy, which is what I have here. Okay. Right. Which is telling us then, right, again, this inequality, dH minus TdS being less than 0 is true for any spontaneous process. So what that's telling me is, right, is the change in Gibbs free energy being less than 0 for any chemical reaction is a spontaneous chemical reaction, right? So you know, all the time in the lab using the idea, oh, the change in Gibbs free energy for this reaction is less than 0, so it's spontaneous, right? That's assuming constant temperature, constant pressure conditions. And when you assume that, right, you get the Gibbs free energy change relates to spontaneity, because that Gibbs free energy change by definition ends up relating to what the entropy change in the universe is. Okay. So for a constant temperature, constant pressure system, okay, the Gibbs free energy change is basically the entropy change in the universe. Okay. It's negative, the entropy change in the universe. Okay. And so a negative delta G gives us a spontaneous reaction, right, which means delta S of the universe is greater than 0. Okay. Right. And again, this Gibbs free energy, we use it, we define it, and it's used all the time in chemistry, because again, chemical reactions are typically done under constant pressure, temperature conditions, right? And then delta G is something we can measure for the system that can tell us about spontaneity under those conditions. Okay. And again, at constant temperature conditions, that delta G is just delta H minus T delta S, which again is a very common form that we've seen for Gibbs free energy. Right. And again, when that's less than 0, something's spontaneous, greater than 0, it's non-spontaneous. And when delta G is equal to 0, your system is at equilibrium. And we'll see that more when we talk about the equilibrium constant and such, probably end up on Monday. So questions again about where the definition of the Gibbs free energy came from, why we define it as it is, okay, what it's telling us. All right. So the question, right, we can ask is, given the signs, the values, whether they're positive or negative, what temperatures will my reaction, say, be spontaneous? Okay. Well, if I have some reaction that has a positive change in entropy and a negative change in enthalpy, that thing will always be spontaneous. Okay. And again, that's always spontaneous because entropy wants to increase and enthalpy wants to decrease for a spontaneous process. Okay. So that will always be spontaneous no matter the temperature. Okay. But if delta S and delta H are both greater than 0, okay, right, that means you're increasing the energy of your system, but you're also increasing the entropy. Which again, now you have one thing that's favorable, an increase in entropy, but then you have one thing that's not favorable, an increase in enthalpy, right? And so it just depends on which one's larger as to whether or not your reaction is going to be spontaneous. And the size, the relative size of these two things, right, is determined by temperature, right? Because I have temperature times delta S compared to that delta H. So only at high temperatures will this favorable process of an increase in entropy dominate to give me a negative delta G, okay, and have that be spontaneous. Okay. Similarly, if delta S is less than 0 and delta H is greater than 0, both of those things are not favorable and not what I want to do spontaneously. And so that process will never be spontaneous. You'll never have a reaction spontaneously occur if the entropy change decreases and the enthalpy change increases. Okay, never going to occur spontaneously. Doesn't mean you can't get that reaction to occur. You just have to heat it up, right, or do something else, right, to it, right. Photoexcite some molecule to get things going, or whatever the case may be, right. You got to perturb the system. We're talking about again something happening spontaneously, right. is what we're kind of talking about here. But there are obviously things you can do in lab to make a reaction that's not spontaneous occur, right? And how hard you kind of force it to occur, right? And then finally, right, if I have a negative delta H and a negative delta S, right, in that case, enthalpy is decreasing, that's favorable, entropy is decreasing, that's not favorable. So only at low temperatures will this process end up being spontaneous. Okay? And what one defines as low versus high temperature really depends on the reaction. Okay, low temperatures could still be like 1,000 Kelvin, right? And the high temperatures could end up being like 5,000 Kelvin or something like that. You know, so the relative value of what high and low temperatures are, it can very much kind of depend on the problem and things like that. But yeah. Okay. So questions about Gibbs free energy, its definition of entropy. All right. So we're going to focus on these things mainly, then focus about chemical and phase equilibria. Okay. And then talk a little bit about electrochemistry. Right. Again, we brushed past entropy and Gibbs free energy in these two brief sections, just again to mainly remind ourselves of these ideas for those who haven't seen them for a while, right? Because right in lab, you know, for this class, I always try to think about like what are more common things to see in lab and papers and stuff like that, right? And so in papers and things like that, you might see things talking about the energy change for a reaction or enthalpy change or entropy change or whether it's spontaneous or not, Gibbs free energy, right? Binding energies are related with kind of enthalpy changes or reactions, right? Sometimes there might be some computations that right, are involved in some paper, and they try to compute whether or not something's spontaneous or not spontaneous, or if it's not spontaneous, by how much, or things like that, and stuff like that, right? So you know, kind of introducing these things here, and then we'll talk more about chemical equilibrium and electrochemistry as well, and how those relate to Gibbs free energy and entropy and stuff. Okay. But any kind of questions about anything we've discussed so far today before we talk about phase equilibrium?
I have a question. It's indirectly related to this thing. Like, if a reaction is thermodynamically stable, does it mean about this equation or spontaneity?
So thermodynamic. So yeah, typically the direction of a reaction that's more thermodynamically stable is the side that has a lower free energy. So it would be referring to what is spontaneously, you know, yeah, the change in Gibbs free energy is negative. That direction is the kind of, you know, direction for the more thermodynamically stable thing, right? And again, to talk about a molecule being thermodynamically stable at, say, room temperature, right? It not being thermodynamically stable means it spontaneously breaks apart to something else, right? Which means it's spontaneously undergoing a chemical reaction, which means that reaction has to have a negative Gibbs free energy change, which means the products, right, are at a lower Gibbs energy than the reactants, okay, for that, say, thermodynamically unstable molecule at a given temperature, right? But often, right, you know, it might be that some molecule is unstable, but you can at least stabilize at lower temperatures because it might be you know, often when the molecule breaks apart, it's breaking apart into more stuff. So its entropy is decreasing, but it might be an endothermic process, right? It might go to a little bit higher energy because you're breaking some bonds, right? And so that's why those things, you know, you potentially get it to low enough temperature and it's not going to be spontaneous anymore in terms of whether or not it's going to break apart, right? For some molecule that might be thermodynamically unstable. By the way, for those who are on Zoom, I know I haven't done a great job of it today, but I'm trying to keep on remembering to kind of repeat questions that are asked in case you guys aren't able to hear the questions from students in class here. But if you don't hear the question and you want to kind of know what was asked or things like that, by all means, just chime in, let me know, and I can repeat the question. But again, I'll try to make sure to do that more often, just because I feel it's helpful for those who aren't here in person to be able to make sure they hear the question, right? But yeah. Other questions? All right, so let's talk about phase equilibria, and we're going to bring this discussion about phase equilibrium and then get to chemical equilibrium, okay, which is kind of more relevant, but okay, so right, so when we talk about chemical equilibrium, phase equilibrium, okay, both of those are going to end up actually fundamentally referring to looking at the chemical potential of some phase. Okay? Now, some of you may or may not have heard this term chemical potential before. Mathematically, it's just kind of related with what is the change in Gibbs free energy with the change in number of moles, okay, of some substance, okay, right, it is referring to chemical potential. So in chemistry, this chemical potential is related with what phase, solid, liquid, gas, what types of solid phases or things like that are more stable, okay? And also, this chemical potential is also related with chemical equilibrium and what things are dominant, whether your products or reactants more dominant at equilibrium, and where is your chemical equilibrium established is related with this chemical potential. Okay. In solid state physics, chemical potential is often referred, it is useful in terms of knowing about where is the Fermi level. If you have two semiconductors next to each other, how do electrons transfer from one to another and form sort of a dipole at the interface and get some partial charge transfer. That's related with equilibrating the chemical potential between the two different semiconductors and things like that, which again are related to what's called their Fermi level and such. And so yeah, this idea of chemical potential does pop up in different aspects of chemistry. So if you haven't heard it before, we'll be using it and discussing it when talking about phase and chemical equilibrium in this class, just because again, it's fundamentally related to why certain things are the dominant phase, why certain things are in equilibrium, and what direction that equilibrium is in, and such is related to chemical potentials. And then, it's something that might pop up in papers that you read and things like that. So it's useful to kind of know what that term is, especially more physics-based work and papers and things like that, or engineering might use chemical potential term more often. I don't think I heard about what chemical potential was until sometime in graduate school myself. It's just the PChem class I took never talked about it. But anyways, so if you haven't heard that term before, you'll hear plenty from me. Okay? But again, the chemical potential is related with kind of this molar Gibbs free energy, right? This change in Gibbs free energy expected to change the number of moles. Okay. Right. So at equilibrium, again, the chemical potential of some substance is equal throughout. Okay. So when you have a homogeneous mixture of stuff, that's you form a homogeneous mixture in order to equilibrate the chemical potential everywhere. Right. You have a chemical reaction that's reached equilibrium. That means that entire reaction, that container, has equal chemical potential everywhere in the container. And reactants, the product side of that chemical reaction. Okay, so again, think of a chemical reaction. It reaches equilibrium when the chemical potential of the reactants equals the chemical potential of the products. Okay, that's when chemical equilibrium is reached. Right, when you're boiling water and you have phase equilibrium between your liquid and your gas phase, that is because at that temperature, at that boiling temperature, the chemical potential of the liquid phase and the gas phase are equal to each other, and that's how you get the boiling process occurring. That's how you establish this equilibrium between the two. Okay. is again by changing the chemical potentials of the species, either by reacting some of the reactants to form products in case of chemical reactions, or say changing the temperature of your substance in terms of like phase change and such. Okay. Right. So, again, to kind of hammer home this point, right? We think about some chemical reaction, right, where I react some number of moles, some small change in number of moles, transfer from 1 to 2, right? Reacting to product. Okay. Right? That change in Gibbs free energy is going to be related with the chemical potential of the final substance minus the chemical potential of the initial substance times that change in number of moles, right? Because I've lost mu1 times dn, worth of stuff in my reactants because I reacted them and formed mu1 dn worth of stuff in my products, right? So this change in Gibbs free energy is related to change in chemical potential times some change in number of moles, okay? And so if you want to be at equilibrium, right, where again, when you're in equilibrium, there's no net change in the number of moles of your reactants or products, no net change in the number of moles in your liquid or gas, right? You're at equilibrium, right, if and only if those chemical potentials are equal to each other, right? Just again, equilibrium is when the Gibbs free energy change is equal to 0, and that only occurs when those chemical potentials are equal to each other. Okay? So again, equilibrium is when change in Gibbs free energy is equal to 0, and then you know you're at equilibrium, and that occurs only when the chemical potential is equal everywhere. Okay? So if I were to plot, say, the chemical potential of the substance in different phases at different temperatures, I'd get the following 3 plots here. Okay? I would get this first line here is the chemical potential for a solid. The second line here is the chemical potential for a liquid, right? And the third line here is the chemical potential for a gas, right? They're all different at different values potentially, except in the cases where it kind of circled here where they cross, right? So what happens, right, is again, the chemical potential is related with the Gibbs free energy of your substance, right? So the lower the chemical potential, the lower Gibbs free energy you have, right? Well, at low temperatures, the solid happens to have the lowest chemical potential, so it is the most stable phase. But as you increase the temperature, okay, right, you're lowering the chemical potential of your different substances, and basically, for salt, like as you go from solid to liquid to gas, an increase in temperature has a greater impact on its chemical potential, right? So you see the chemical potential for solid is relatively flat with temperature. For liquid, there's some slope to it. For gas, there's a very steep slope, right? The chemical potential of gas with respect to temperature. Okay? And so because of the fact that these different phases have different dependence on temperature for the chemical potentials, right? You go from a solid at low temperatures to a liquid at, say medium temperatures, if you will, to a gas phase at high temperatures, right? And then phase equilibrium occurs when these 2 chemical potential lines intersect. Okay, point where those 2 lines intersect is where your phase equilibrium occurs, right? And then if you move to the left or the right of that phase equilibrium, you either have the liquid, say, or the gas phase, the solid, or the liquid phase, and it being the dominant phase at that temperature. And the temperature in which these phases equal each other, these chemical potentials, right, is that phase transition temperature, right? So I have that TF for the first point of intersection, that's at freezing temperature, TB, right, boiling temperature. Okay. Right. Just kind of reiterating again that that transition temperature, right? You have 2 phases that are in equilibrium, okay, and they're in equilibrium because their chemical potentials are equal, okay. And you could, for example, get something into a phase that is not the lowest phase, right? So let's say, all right, I have something in the liquid phase, right? I could tend to cool that liquid lower than the freezing temperature and remain in the liquid phase if I do things in a very slow, methodical way. I can potentially get my liquid to be kind of a super cooled liquid, right? A better way to think of this is with dissolving things, right? If you remember from like general temperature stuff, right? The idea is super saturated solution, right? I can have a solution at a higher temperature that has a greater saturation limit, and I can slowly cool off that system and keep all of my solid dissolved, and I form a super saturated solution. That is a metastable phase, right? It is not at equilibrium, and any slight perturbation to that super saturated solution will get a bunch of the solid to crash out and form in that solution, right? And so the same thing can happen with just a pure substance and going from solid liquid to gas, right? And different compounds have different number of phases, especially in the solid phase. You can have multiple versions of the solid phase, right? Carbon, an easy example, graphite versus diamond, right? Graphite is one form of solid carbon, diamond is another form, right? Technically, at room temperature, diamond is a metastable phase because it has a higher chemical potential than graphite, right? But even though it's metastable, right, meaning it's not technically the thermodynamically favorable phase, doesn't mean diamond will spontaneously form carbon immediately, right? The diamond in jewelry is not going to all of a sudden form graphite after a couple of years or something like that, right? And this point is just here to reiterate the idea that even if something has a more thermodynamically stable form, okay, right, doesn't mean kinetically it is likely to reach them, right? And again, this is just to emphasize the difference between thermodynamics and kinetics, right? Kinetics, right, telling you how long it takes to get to your final state, right? Thermodynamics tells whether or not it's spontaneous, but just because something is spontaneous doesn't mean it takes a short amount of time, right? Something that's spontaneous can still take a very long amount of time, especially if there's a large activation barrier for that, right? Again, the example of diamond forming graphite, right? Even if graphite is more thermodynamically stable, right? Not by much, but by a few kcals or so. Diamond is less stable than graphite. You know, you've got to break a bunch of carbon bonds, right? And before you can get from diamond to graphite, and breaking those bonds requires a lot of energy, and so it's just not going to happen spontaneously. It will not happen in any time scale that we need to be concerned about, right? And so that's always kind of a weird thing to wrap your head around. Is just that you know, I can say diamond going to graphite is a spontaneous reaction, but it's not like, you know, but we think of spontaneous as facts, right? And that doesn't mean the same thing in thermodynamics, right? Spontaneous and speed fast doesn't mean the same thing. Okay? Let me see here, quick kind of where we're at, running all on time here. Yeah, we can talk just briefly about phase diagrams. Yeah, so let's just talk about phase diagrams to kind of wrap up today. Right, just to remind ourselves, phase diagrams, right? Hopefully, you know, these things are very familiar by now. Your chemistry career, right? You got your solid, liquid, vapor phase in your phase diagram, okay? Right. And then these lines correspond to phase boundaries, right? Where both phases are in equilibrium, okay? And the point here, this triple point, right, is when all three phases happen to be in equilibrium, okay? Right. You can use these phase diagrams to get boiling temperatures and boiling points and things like that, right? So at 1 atmosphere, I can look at what is the boiling temperature of my liquid by drawing the horizontal line from 1 atmosphere to the phase boundary between the liquid, okay, and the vapor, and then going down to get the temperature in which that phase boundary is at that pressure, right? Because again, the boiling temperature of some substance is related when the pressure of that liquid, the vapor pressure of your liquid equals atmospheric pressure, right? And so, right, that liquid vapor phase boundary is telling you what is the vapor pressure of that liquid at a given temperature, okay? So this phase boundary is like the vapor pressure of the liquid, right, in a temperature versus pressure plot. This is the vapor pressure of the liquid at a given temperature, okay? And so I can use, if I want to know what's the boiling temperature at a certain pressure, right? I can use this phase boundary in order to get what that boiling temperature is, because I can just, say, okay, that boiling pressure, the pressure of my liquid has to equal the external pressure, right? And so I draw a horizontal line at that pressure, find where it equals the vapor pressure of the liquid, which is at the phase boundary, and then go down to get the temperature. Okay? Right? And again, as I mentioned, right, the certain substances like water can have multiple phases. Okay, for example, water has many different solid phases that have been both experimentally and some theoretically kind of discovered. Okay, and note here that only 3 phases can at most be in equilibrium at a time. Okay, so there's never 4 of these phases meeting at the exact same point. At most, 3 phases meet at a specific point at any different location in this chart. Here. Okay. Questions about kind of phase diagrams, how to interpret them, how to use them. Fairly single component systems. So next time we'll talk about kind of how we locate these phase boundaries, how we study them and things like that, to introduce some of these equations. As these, say this Clausius Clapeyron equation will come into, that will be very similar to the equations we'll derive and talk about with chemical equilibrium and temperature dependence and equilibrium constants, things like that, will all be related to kind of some of this discussion here. So we'll talk more about the thermodynamics of phase equilibrium next time. Okay. I want to make just a brief note and announcement in the last minute or two here in class. Just state that so recently well, not recently. So this is going to be my final year here at Texas State, and so as part of that is looking for new employment opportunities, and one has kind of come up spontaneously in a lot sooner time frame than I was expecting. So I will be leaving before the semester ends. So someone else will take over this class from me. It's likely someone that the department is going to be hiring to teach this semester to cover my classes, just because typically the faculty here already are at full workload. So like Dr. Rhodes isn't going to be picking this up because he's already got a bunch of classes he's got to teach, other things he's got to do. So I will be around until that person gets here and is able to get settled and get ready to go. It's likely to be sometime early mid-February when that transition is going to occur. What else? And there's a good chance, not guaranteed, but a good chance that person, when they're starting, is potentially going to want to just do things online completely. I don't know. Or in person completely. I don't know how they're going to do it. It takes some more time and effort, depending on how you structure the class, to do it both in person and online. How I'm kind of doing this class, it's not that difficult, but but I don't know. So there could be some changes that occur with someone else coming in to take over the class. But they're not going to change a lot of things in the syllabus in terms of kind of number of exams and things like that. I think the biggest change could just be if that person only wants to teach the class online because they don't feel comfortable doing things in person. And so that might be the biggest change that occurs in the class, is just that. But otherwise, things shouldn't be changing too drastically from how I would do it, because they'll likely just use my lecture notes and other things like that, and kind of modify some of my old exams or things like that. So, but there'll still be the presentations at the end of the semester, and I'll give them the grading rubric that I have for that. And so again, there won't be major changes in how the course will work, besides potentially, whether or not it's completely remote or not. That would be up to the professors how they feel about doing it. Okay. So any questions about anything kind of we talked about today and such before we head out? Okay. All right. Well, like I said, I'll stick around. Got a minute or two left, but so if anyone has any questions, welcome to ask me. there over Zoom here in person. Otherwise, I will see you guys on Wednesday. When I have a more determined date about when my last day will be, I'll let you know. But as of right now, there's not quite a set final date.